So guys, in this class, we will be uh, learning about the clipping, which is part of our third module. So what do we mean by clipping? Before we enter into clipping, we will be looking at what do we mean by clipping window, and then understand what is clipping, and then look into point clipping and what do we mean by line clipping. After that, we'll be looking at a specific algorithm called as Cohen Sutherland line clipping algorithm, and we will see an example problem to solve using Cohen Sutherland line clipping algorithm. So clipping window. Now you see, guys. Say suppose we have a world out there. Imagine. um this is my world, right? I don't want to see this. Sorry, I don't want to see these part of my world. I just want to see this much portion of my world, right? That I can do, and I can do that by using an window called as clipping window. So in the program, by now you guys have using while you're implementing programs in OpenGL, you guys have seen. Um, Using GL ortho 2D, right? And we specify a window in our world in which the objects have to be visible. So that window is called as clipping window. Just to give you an idea, right? Whatever the say in this world, if this is my clipping window dimension, then whatever fits into this window in my world is what will be visible on your display window. Now I'll give you a small idea or example of how this works. Okay. Now you guys are able to see in your devices, you guys are able to see this slide, right? Now imagine the slide itself is my world. I'm able to see, display it completely. I want my world completely to be displayed. So I have set my clipping window to the complete slide, and that clipping window is what is displayed into your screens. Now your screens is analogous to or equivalent to your display window. That is the one that you create using glut create window. The what you are seeing, imagine that is your hardware output, right? That you are seeing as your output. Now whatever you see in the output is the content of the world which fits into this clipping window. So if I want you to see this complete slide, what I'll do is I'll set my clipping window equivalent to this world. Now say suppose I don't want you to see that much, I only want you to see this area. Now you see there is a bigger world out there. I am not seeing, you guys are not seeing it. We all know that there is a lot of objects in my world now, that is in the slide. But because I have limited my zooming window to this, the highlighted rectangle, I am only able to see this much portion of my world in the display window. The display window size you're not changing, you just varied, you change the size of your clipping window. The clipping window earlier size was the window, the slide size, the complete my desktop size. And now when I applied zoom, I changed my clipping window size. And that's the whole idea of clipping window. I hope you guys are clear with this. All the parts outside the selected section or the outside the clipping window are clipped off, meaning to say the graphics library has to come up with a way to remove it from the display or from the scene, because graphics library you have supplied the definition of the complete scene. But when it has to display that scene to your device, it has to come up, it has to show only the amount of scene that is there in the clipping window. Again, clipping window is defined by you, the programmer. Now that clipping has to happen. Clipping meaning to say this removing this portion, unnecessary portion, whichever is outside the clipping window, so that activity is called as clipping, and this window what we select here is called as clipping window. Now, so graphics packages commonly allow us to use a rectangular clipping window. Technically, theoretically, we can consider this clipping window not just as a rectangle. We can consider it in any dimension. For example, if I consider here rhombus shape as my clipping window, only this much portion has to be displayed into my uh, output window, right? But there is a complexity that involves if graphics packages has to allow all kind of shapes for clipping window, so we are limited by, usually they support only rectangular clipping windows. This clipping window sometimes is also called as viewing window. So clipping, as I told, the procedure that eliminates the portion of the picture or the scene that are outside of a specific region of space is referred to as clipping. Over here, the specific region of space that we define is called as clipping window, the window that we discussed in the earlier slide, right? So clipping is basically used to extract the portion that is inside the window and show that scene onto the output device. Output device here in our context is nothing but your display window that you create using glut create window. Now, clipping algorithms are the algorithms that you use in order to, to remove the portion and to which is outside the clipping window and to retain the portion which is inside the clipping window. So there are two types of clippings that we consider as part of our syllabus, that is point clipping and line clipping. Point clipping is quite simple and straightforward. Line clipping has many ways to do it. One way is Cohen Sutherland algorithm, which we're going to discuss. That is because we it is part of our syllabus, but there are also many clipping algorithms available out there. You guys can refer it. In fact, in your reference or prescribed textbook itself, there are multiple line clipping algorithms. You guys can look into it if you want to. Imagine that we have a rectangle or a clipping region that is defined by boundary xw min, xw max, yw min, and yw max, uh, something like this: xw min, xw max, yw min, and yw max. The point clipping is quite straightforward. We take the xy coordinate points of this and see that the xy is in the limit of this. It satisfies this equation. If it satisfies, then we don't have to clip that point, meaning to say we have to retain that so that it is displayed. If it doesn't satisfy any one of this condition, that means that that point is outside the edges of the window and we have to clip it, or we have to eliminate it or reject the point from displaying. So say suppose over here, this one, this y, x comma y, imagine this has a coordinate as x comma y, this should be less than y min, sorry, this should be greater than y min, but this is less than, sorry, this should be greater, the x of this should be greater than x min, but this x is smaller than x min. So one of the condition out of these four conditions are not satisfying, so we reject this point. Over here it is greater than x max. However, we expected x should be less than our x max, or for this point x is greater than x max, so we reject this. This point, the x and y coordinates of this point satisfies all these four conditions, so we won't clip it, meaning to say we consider this point to display it. So this way, two-dimensional point clipping is quite a straightforward approach. Two-dimensional line clipping. So imagine we have lines something like this. This is my clipping window. We have a bigger world out here. There is a line like this in the world. There's a line like this in the world. There's a line like this and like this and like this in the world. This is my clipping window. So if I perform clipping, the clipping algorithm should eliminate this line because this line is completely out of my window. Should eliminate this line because this line is again completely outside my clipping window. Should retain this line completely because this line is completely inside the window. Should clip this line, meaning to say it should remove this small portion over here from the display, and it should consider the line from P6 to this intersection point of the left edge of the clipping window to this line. So let's say this is P5 dash. So the line that has to be displayed on the screen should be from P6 to this intersection point P5 dash. So this is clipping, and this is also clipping. It removed completely, it retained. However, over here it found a intersection point. For this line, the intersection has to be computed for both the points with respect to both the points. Here the intersection had to be computed with respect to only one point because the other point was already inside the window. Over here the intersection has to be done with respect to both the points because both the points are outside the window, but the line itself is partially inside the window. See here, over here also both the points are outside the window, but still the line is completely outside. It is not passing through the window, so we don't need any kind of computing the intersection. We just upfront right away discard the line. Over here we have to compute this intersection and then this intersection and then consider this line and eliminate the line portion from P8 to P8 dash and P7 to P7 dash. So this is the idea of line clipping. So the main goal of any line clipping algorithm is to minimize the intersection calculation, meaning to say I have to reduce the complexity of calculating, coming up with a way to find this intersection point. So that's the idea of two-dimensional line clip.
We will get started with Cohen Sutherland line clipping algorithm. So Cohen Sutherland line clipping algorithm is actually quite faster in clipping. The reason is we consider bitwise operation. We make use of bitwise operation extensively in this algorithm. So to start with, what we do is consider this is my clipping window. So I divide my clipping window, the area, the 2D space in and around the clipping window, into the 9 regions like this. So I extend my top edge, right edge, left edge and the bottom edge. So that divides the 2D space into 9 regions like this. So after dividing this, what I do is I assign bit positions to different regions. So I use bits. So I take 4 bits, a 4-bit variable like this, and I assign using the notation. I assign, I use the first bit to represent the left side. I use the second bit to represent the right side. I use the third bit to represent the bottom side. I use the fourth bit to represent the top side of the window. So using this bit representation, I go on assigning bit bitwise, codes for all these regions. If you see here, this region is towards the left side, right, of the clipping window. So since it is towards the left side of the clipping window, what I do is I set the bit which is responsible for, which is representing the left side of the clipping window. If you see here, over here also, this left side is set. The reason is these two regions are also towards the left side of my clipping window. Similarly, if you see here, the fourth bit here is representing the top region. That's why, since this area is in region is in top of the clipping window, so I set this bit. Even in this, I set this bit. If you see, this region has the code 1001, meaning to say, since top bit is set, it is in the top, as well as since left bit is set, it is in the left. So likewise, I go and assign all these region codes for these 8 regions around the clipping window. Now inside the clipping window, if you see it, the inside clipping window doesn't belong to left or right or bottom or top regions with respect to the clipping window. So that's why I consider the default value as 0000. Now these bit representations are called as region codes. So over here, what we do is we take region codes to we assign region codes to all the 9 regions, including the clipping window, and then we move forward. To start with, in Cohen Sutherland algorithm, we assign region codes is basically the first step. If you see, this is left, this is bottom. If I consider the left side region code, and if I know the bottom region code, I can easily get this region code. I don't have to go and assign it. I can derive it based on left and bottom code. This region code is the R of left as well as bottom. So bottom left region code is the result of R of left region code and the bottom region code. This is something that we have to remember. So moving forward, what we do is the next step in Cohen Sutherland line clipping algorithm is we set region codes for all line endpoints, or we also call them as out codes. So consider I have a line like this. I take an endpoint that is over here and I assign something called as out code to this point. The out code of this point is same as the region code of the of where it is residing. Since this is residing in the bottom region, the out code of this endpoint, let us say this endpoint is A and this endpoint is B. The out code of endpoint A is basically the region code of bottom because it is in bottom region. So I assign 1000 to this. Similarly, the out code of B is same as the region code of the top region. So the out code of this B endpoint is 1000. If I take a point here, the outcode of this point will be 0010. The outcode of this point will be 0110. So if there is a region inside like this, then the outcode of this point, since it's inside the clipping window, it becomes 0000, and this also becomes 0000. Let us say this line is extended like this, then the outcode of this is 1000. The outcode of this is 0000. So this is about assigning endcodes to the endpoints, assigning outcodes to the endpoints of the line. So the first step that we do is we assign region codes. We divide the 2D space into different regions, and we assign bit codes called as region codes into these regions. And then we take lines. We consider the endpoints of the lines, and depending on which region the endpoint would reside, we assign outcodes to those endpoints depending on the region code in which it is present. The next step that we do is, see, once we know the endpoints outcodes, we can perform 2 tests and decide on 2 things very easily. First thing is, I can, if I know the endpoints or region codes, sorry, the outcodes of the endpoints, I can easily test and decide if my line is completely inside the clip window, or I can easily decide if my line is completely outside the clipping window. Now, how do we do this? We do this using certain bitwise operators. Let's look at what happens, right? Let's say this is the line which resides completely inside the clipping window. Now, how do I detect it? Now, if the region code is 0000 for both the endpoints, meaning to say if this outcode is also 0000, if this outcode is also 0000, then I can decide that it is, this line is completely inside, and so I accept this line. Accept this line is nothing but I consider this line to display in my clipping window. How do I determine if it is both of them is 0000? Simple. I perform bitwise OR operation. If I use bitwise OR operation, then since both the outcodes of the endpoints will be 0, the bitwise OR will always give me 0. So basically, if I perform OR operation, no other regions, if my line is something like this, or if my line is this line or this line, OR operation will never give me true. It will always it will never give me false, it will always give me true, because if you see, all the other 8 regions have one bit set, one or the other bit set. Only this inside region have all bits set to 0. That's why only if both the points are inside the clipping window, the bitwise OR operation would give me false. So if it is 0000, meaning to say it is false. Now that is one way, that is the way I can easily determine if my line is completely inside the clipping window or not. So what I'll do is, initially I'll assign the region codes, and then I'll compute the end code, so lines endpoints outcode. After that, I perform OR operation between these outcodes. If OR operation gives me false, then that means to say I my line is completely inside. So I stop the algorithm also. I stop my algorithm and I accept the line to draw it inside the clipping window. So this is all. This is one of the stop condition that I can use. If this condition occurs, that means my line is completely inside. It further needs no clipping. It needs no clipping at all. So I can stop my algorithm easily. The other thing is, say suppose if the line resides on the same side of the same region, same side of the clipping window. Over here, this line is residing on the top, right side of the clipping window, and this line is residing on the bottom side of the clipping window. So, because since it all both the points reside on the bottom, this bottom bit is always set. Similarly, since this resides on the right side, the bit that represents the right side of the clipping window is always set. So now, if the region value of 1 is same bit position is in the so 1 is in the same bit position for the endpoints. So basically, if all the both the endpoints have same bit position set, then I can completely tell that, easily tell that my line is completely outside the window, and I can reject my line because it is outside. I don't have to write it in my clipping window. That's why I reject this line. So how do I determine? To determine that, what I have to do is I take the endpoints of the line and I perform bitwise AND operation. Now see, I take 0, the outcode of this point is 0, 1, 0, 1. The outcode of this point is 0, 1, 0 and 0. The AND of this will give me 0, 1, 0 and 0. Similarly, take the output of this line and this line. So and apply AND of it. The result of AND operation between the output of those two endpoints will give me 0, 0, 1, 0. Now, see, observe the output of AND operation. If the line completely resides outside on one side of the clipping window, then the AND operation will always give me true. So this is the true operation. In this case also, this is one of another stop condition for us. I stop my algorithm and I decide that this line is completely outside the clipping window and I reject the line. So basically, to summarize, I perform AND or OR operation between the out codes. If this gives false, then I accept my line and I stop my algorithm. Similarly, I apply if this produces true, I move forward and I apply AND operation to see if I can reject this line straight away without clipping. If this produces true, then I reject the line and I stop my algorithm because I don't have to draw that line at all. So these both conditions acts as stop conditions for this algorithm. So to start with, in the algorithm, I assign region codes, I compute the endpoints out code, and then I take the out codes of the endpoints of a line. I apply OR operation. If it is false, I stop it. If not, I move forward and I apply AND operation between those out codes. If true, I stop the algorithm and reject the line. Here, if it is true, I accept the line and then stop the algorithm. If it is false, I stop my algorithm and accept the line. If it is true, I move forward and I apply AND operation. If it is true, I reject the line and stop my algorithm. If this becomes false, then I move forward. So if this becomes false, that means this line is not completely inside or not completely outside. It might be completely outside, but it might be present in different region. The endpoints might be in different region like this, or it might be something like this, which mean to say it needs clipping. So to do this, we need to further perform clipping. Clipping meaning to say we have to check for the intersection with the window border lines. To clip this line, I have to find the intersection with this window borderline bottom. To clip this line, so I have to find the intersection point here and I have to find the intersection point here with the top line and here with the bottom line of the clipping window. Now for this also we need clipping. Actually, we can't straight away reject it because if you see, the OR operation gives me true and AND operation gives me false for these endpoints. So I will still have to go and do the clipping. So what will I do is I either I calculate this intersection point. uh, I can calculate this intersection point or this intersection point depending on what order I am going. I am for now argument's sake considering this intersection point. After doing this, I consider this line, and now if you see the output of this line and this line, the top bit is set. So since after clipping it one time, because the top bit is set between this new point's output and the old point, that is this point, the AND operation would give me true and I can stop this algorithm and reject this line. So this line gets rejected anyway, but still it cannot be rejected in the beginning itself because it resides in the across two regions. Uh, so I'll have to perform clipping at least once in order to reject it. So we'll move forward and see how the clipping is performed. So the clipping is, if we decide if this condition fails and if this condition fails, we move forward for the algorithm to perform clipping. How we perform clipping is, now imagine this is the line. So the line was something like this. If this was the line, then the outcode of this is 1001 and the outcode of this is 0100. This condition fails, this condition fails. So how about going for the clipping now? Now what I'll do is, I'll take one of the endpoint, either P2 or P0. Consider I'll take P0. The P0's endpoint was 1000, sorry, 0100. Now I'll take this P0 and I will see if this P0 is in left region. So I set an order of evaluation now. Let us say I am going in the order left, right, then bottom, then top. I can go in any order, but one order has to be fixed while I am running my algorithm. So I have to perform all the operations in the same order. Let us say I am going in this order, left, right, bottom and top. So first I'll take the outcode of this point and I will take the region code of left, and then I perform AND operation between them. Since if you see, this will, the left region code will be 0001, the AND operation will give me false. So if the AND operation between the region code and the outcode of the point is false, that means that point is not in that region. So that is what I do with left region. I take this outcode and I take the left region's outcode, perform AND operation. Then since it is false, P1 is not in the left region. Then I take P1 and I go to my next region, that is right region. I take the right region's outcode and I perform AND operation, and then I figure that P1 is not in the right region because the AND operation of right region outcode and the outcode of this point gives me false. Then I take P1 outcode and I go to the next region, that is bottom. I'll take bottom region's outcode and I perform, bottom region's outcode was 1000. I perform AND operation. This gives me true. Because it gave me true, it means that this point is in the bottom region. Now what we do? Now if it is in the bottom region, if AND operation gives me true, then I'll consider the line which is the bottom line, that is, in this case ymin is the bottom line which is separating the bottom region with the clipping window. So I clip this line by taking the intersection point of this line with the bottom line, because this bottom line of the clipping window is what will identify or will separate the bottom region with the clipping window. I consider my bottom line of the clipping window. I take this intersection point and now I call this intersection point as P1 dash. Now what will I do? I will ignore this portion. I'll delete this portion, meaning to say I'll take the line from P2 to P1 dash and I repeat my operation. I'll calculate the outcode of P1 dash. If you see, P1 dash will be exactly on this line. So it will not be in the bottom region, left region, top region or the right side region. Though P1 dash outcode will be 0, 0, 0 and 0. Since this outcode became 0, 0, 0, 0, I don't have to further clip this point. Now I take the line from P2 to P1 dash and I do the clipping. P1 dash does not need any clipping. So the next point that I need to consider will be P2. Now I'll take my P2 point. Again, I will process it in left, right, bottom and then top order. So I'll take P2. I'll repeat the same step what I did with P1. I'll see if my P2 is in left region. Since it is in left region, the left region separator is this X-min point of the clipping window. So I calculate this intersection point. I call it P2 dash. Now I calculate the P2 dash outcode. I'll calculate the outcode of this. The line that I will consider now, P2 to P2 dash will be eliminated. The line that I will be considering now would be P2 dash to P1 dash. Now I'll calculate the outcode of P2 dash. So the P2 dash is in the top region. So the outcode will be 1000. Now this 1000 with the, I already did it with left. I'll go and see if it is in the right region. It is not in the right region. So I'll go to the bottom region. It's not in the bottom region. So I'll go to the top region. If you see, the top region's outcode and the P2 dash outcode is same. That's why I need further clipping with respect to the top edge of the clipping window. So I'll take this line P1 dash to P2 dash and find the intersection with this top edge, and I'll call it as P2 dash. And then I'll calculate the P2 dash outcode. This outcode is also will also become 0000 because it will be inside, and I'll repeat it. This is also already 0000. Now the line under consideration is P1 dash and P2 double dash. Now if you see, the OR operation between these two is, this is the stop condition. The OR operation will give me false. Since it gives me false, I stop my algorithm. So this is my Cohen Sutherland algorithm, guys. So we will see an example of how this working is done. Before that, we have to see how this intersection point is calculated, right? So now to determine the boundary intersection point, consider this line. This line is starting from x0, y0 to x end, y end. The slope of this line is this. Now, say you want to calculate the intersection point with vertical clipping border. So vertical clipping border is this and this, right? So this is identified by xmin and this one is identified by xw max. This is identified by sw min. Now, what will be the x of, so if this intersection was to be computed, the intersection with the vertical clipping border at the minimum, that is at xw min, if you are calculating, then the x of this intersection point will always be xw min only, no? Similarly, if you are calculating with the line intersection of this line with xw max, then the intersection of this point will be xw max. So if you take x comma y for this, and if you take x comma for y, if you take for this, the x of this will be either xw min or xw max. What about y? I can say the slope of this line or this line is equal to the slope of this line. So I can say that y minus y naught divided by x minus x naught is equal to m, where my m is yn minus y naught by xn minus x naught. So using this equation, I can calculate my unknown term here. My x will be known because if I am doing with left edge, then I'll have xw min here. So, or if I am doing with the right edge, then I'll have xw max here. So thereby using this relationship, I can calculate y, and depending on if I am clipping with respect to left edge or right edge, I can calculate my I can easily find out my uh, x coordinate value of the clip point. Similar to this, using the same relationship that m is equal to y naught minus y naught divided by x minus x naught will be equal to m. If I see the intersection point with the line with the horizontal point, then the y of this line will be y min and the y of this line will be y max. So y min and y max, and using the same relationship, that the formula that I discussed earlier, the x can be found out here, but the y will be depending on if I am clipping with top edge or the bottom edge, y min or y max. So slope as usual will be the slope of this line. So using this formula I can calculate my intersection points. So now before even going to example, I'll just repeat what we have to do. So I'll set up the region codes and then I'll calculate out codes of the endpoints. I'll perform R and see if it is inside. If not, I'll move forward. I'll perform and see if it is completely outside on one region. If not, I'll move forward for clipping. So if true, I stop it and accept the line. Here, if this condition becomes true, I stop it and I reject the line. If not, I move forward. I move forward and I consider one point and see if it is in any of the four regions. To which, in whichever region it is, I'll clip the line by calculating the intersection point with that particular edge of the clipping window and the line. That intersection point outscored again I'll calculate and I'll move to clip again and again. I'll keep doing the same until this becomes 0 or this becomes 0 or the line goes completely outside. So we'll see an example. Perform Cohen Sutherland line clipping algorithm for a given clipping window on the line segment. So the clipping window, x min and y min is given as 50-50 and x max and y max is given as 100 and 100. The line segment is between 60-140 to 80-10 or 80-10 to 60-140. Let's see how to solve this problem.
So these are the given data to me. I know these 2 points and I know my minimum and maximum boundary of the window. So basically I know the details of these points, coordinates, and I know the boundary of this window. And the very first thing that I'm supposed to do is I'm supposed to assign region codes as the first step of my algorithm. So the region code that I have taken here is same as that of what we discussed earlier. You can go for different region code also. For example, you can represent top first, sorry, then yeah, bottom, and then left, and then right. You can go like this. There's no problem, but you have to stick to this notion, bit representation throughout. So I have stuck to this thing, top, then bottom, and then right, and then left notation is what I am going with. So according to that, I have assigned my region codes. Now the very first step that I'm supposed to do is to calculate the region codes, out codes of my endpoints. So for P naught is this point 80 and 10. So to check in which area this is it in bottom or right or left or top, what I do is I take my x naught value and I compare and see if it is greater than my x naught towards this side. If yes, then it would be towards the right side. If it's less than my x min value, it will be left side. So since these two are false, so it is not on right side as well as left side. Similarly, I'll take my y naught and I'll see if it is greater than y max, my 10. So that is for this point, the y naught I'll take and I'll see if it is greater than my y max. Since it is false, it's not in top region. Similarly, I'll see if it is in bottom region by comparing it with y min, I'll see if my y naught is less than y min. It is true. That means it is in bottom region. So since it is in bottom region, to p naught, I'll assign the outcode of bottom region. So I got 0, 1, 0, 0, and over here also it is 0, 1, 0, 0. Similarly, I'll take outcode of this point P naught and I'll see compare it with all the four boundaries of the window. So I get right as false, left is false, and bottom as false, but the top as true. 130 is greater than 100 is true. Over here 10 less than 100 was true. So this is in top region, and similarly this is in bottom region. So since my P1 I concluded that it is in top region, I assign the outcode of top region to it. So it gets the outcode of top region. Next thing that I am supposed to do is the step 2. I have to see, now I have the outcode of both these points. I have to see if I can accept this line or reject this line straight away, concluding that it is either completely inside or completely outside on the one side of the window. So for that, I have to perform an OR operation. If it gives true, then I could have concluded that it is completely, sorry, if it gives false, I could have concluded that it is completely inside. Since it's giving me true, I can't conclude that it is completely inside. So I get to know that my line is not completely inside. Next thing is I perform AND operation between these two. If I get true, I could have concluded that this line is completely on one side of my window and that is outside. But since I did not get it as true, I got it as false. That means the line is not completely outside on a single region of the window. So since these two steps failed, now I have to go and do the clipping, meaning to say I have to go and perform uh, clipping, compute the intersection with respect to some boundaries of the window. Now to do that, what I'll do is I'll initially take one point, that is P naught, and start processing it. So considering P naught, so this is the outcode of P naught, and since this outcode and bottom, right, bottom meaning to say the bottom outcode, the bottom outcode is true. So algorithmically, I should have seen this OC naught and left and top and right also to figure out in which region it is. Since the AND operation gives true for bottom, P naught is in bottom region. So since it is in bottom region, I have to clip the point P naught with respect to the bottom edge or the below edge. So if it's in the bottom edge, this intersection points y will be y min always. So I have taken y is equal to y min. So x is equal to x naught plus y min minus y naught divided by m. This is the same formula that we discussed while, for calculating the intersection. This one. So I plug in x naught value, y min value, y naught value, and the slope of this complete line that I have calculated, p naught to p1 line, I have calculated the slope of it -6, and I have plugged in that value also. So the result I get is 73.33. So therefore, the clip point is 73.33 comma 50. So I name it P naught dash. My P naught dash, that is intersection with bottom edge, is 73.33 comma 0 comma 50. Now the line that I am supposed to consider is P naught to P1 to P naught dash. Now after considering this line P1 to P naught dash, I have to repeat the step. So my step 1 was to calculate outcode of the endpoints of the line. Now I'm considering this line P1 to P naught dash. I have to compute the end code of it. I don't have to compute the end code of this. I'll only compute the end code of this because I already know the end code of this. So end code of P naught and P1, P naught dash and P1 is what I'm supposed to calculate. So P naught dash outcode, if I have to calculate, I would get everything as false. So all these values are false, meaning to say it's inside the uh, clipping window. That's why I assign the inside region's outcode, that is 0000. Since outcode of PC not P naught dash is 0000, so we conclude or we figure out that it is completely inside. What is completely inside? Only P naught dash is. So next thing, we already know that P1's outcode is same as that of the top region. Then what we do? We do step 2. Step 2 is to see if this new line that we got is completely inside or completely outside. Since the OR operation gives true, it's not completely inside, and since AND operation gives false, it's not completely outside. Again, I'm supposed to perform clipping. Now see here, once I was done with step 2 here, I had to pick one of these 2 points and do further processing. That is, I picked P naught and went and checked it is intersecting with which region, which edge, and I figured out the intersection point. Now, the same thing I have to do it here also. I have to take one of these 2 points, and in this step, I could have pick P1 and proceeded. In that case, I would have got this intersection point, right? So the order, it doesn't matter in which order you process P naught first and P1 first or P naught first. So in this example, we are considering P naught first, and we got P naught dash as our intersection. Now we are supposed to take one of these 2 points and then perform clipping by checking if it intersects with with which edge of the clipping window it intersects with. But to take this P naught dash, it's already 0000, right? So it's already inside. So I don't have to check with check if this point is intersecting with any of the edge. Because it's already inside. So in that case, because of that, I'll consider my other point, that is P1. P1's outcode is this. Since outcode of P1 and top region code gives true, I conclude that P1 is in top region. Now, since P1 is in top region, I have to clip it with respect to top edge. That is, I have to find the intersection with respect to the top edge. Since this point is intersecting at the top edge, the y of this point will be always 100. So that is the y max. And then I plug in x naught and y naught values and y max value, and the slope that I am considering here is the slope of the new line, that is the slope of this line. So if you see here, I have even if I take the slope of the new line, okay, in this case I have taken the P naught point itself. Even if you take this as 73.33, right, and this as 50, you would get the same slope as the actual line that we had, so there is no issue. Now I plug in these values, I get my x as 65. So the intersection point P1 dash that I get is 65 comma 100. Now the new line that I have in my hand is P naught dash to P1 dash. So I take this point, this line, and I repeat my step. So I go to P naught dash and P1 dash. I already know, so I am supposed to do the step 1, that is calculating the outcode of these 2 points. Since I already know I had calculated the outcode of PO naught, and the outcode was 000. I already know this. I am supposed to calculate the outcode of P1 dash alone. So P1 dash is this. So if I compare, all of them gives me false. Because of this, even P1 dash, I conclude that it is inside, and I assign the region code of inside the rectangle. The next thing is step 2. I have to see if the line is completely inside or outside. So since the OR operation of these two outcodes gives me false, I conclude that the line P0 dash and P1 dash is completely inside the clipping window, and I stop my algorithm, and I will in the output plot the line from P0 dash to P1 dash. So therefore, after clipping, the points that I got for the line is P0 dash and P1 dash, which is 73.33 comma 50 to 65 comma 100. These two are the example problem for you guys to solve. So you can consider this line and this line also, and then perform clipping and give me these intersection point. In this case, you are supposed to accept this line. In this line, you are supposed to reject it. But since this line is lying across different region, not in the same region, you cannot reject it in the single shot. This will get top outcode region, and this will get left region outcode. This will get top region outcode. So the AND operation will give you false actually. So because of that, what you will have to do is you will have to compute, you know, the intersection point, either this one, or if you clip it with a top edge, either this one. In either cases, so the outcode of this point or this point will have the bit for top as set. So after you clip it and you get either one of these intersection point, if you apply AND operation between this point and the top point, either this point and this point, or the this point and this point, if you apply AND operation, that will give you true. So you can stop the algorithm and you can reject the line completely. So that's about Cohen Sutherland line clipping algorithm, guys. Thank you.